Good day, worldwide university students. Welcome to the channel of Massive Quality Mathematics, where we abuse mathematics by finding solutions. Today, I want to take you through the course called Linear Algebra, specifically through the topic called vector spaces, as projected on the screen. So under the course Linear Algebra, I will make several videos covering the following topics or subtopics: vector spaces and subspaces, inner product spaces, linear transformation and diagonalization, eigenvalues, eigenvectors and orthogonality, matrices, determinants and inverses, and many more. So feel free to inquire anything about the course. You can write your questions in the comment sections, and I promise your questions will be highly considered and responded in due time. So we can go through the course. Now we'll start with an introduction to vectors. So in the early grades or high school, those who studied, obvious, if you are doing mathematics, you studied maths and science in lower grades. So we talk about physical science, they talk about vectors and scalars. So the traditional difference between a vectors and scalar is direction. So we used to define a vector as a physical quantity that has both magnitude and direction, but a scalar is a physical quantity that has magnitude only. So these are the basic principles that are distributed in high school. So now I want to take you through introduction to vectors. You know the notation of vectors. So the notation of vectors can be what called any letters with an arrow on top showing the direction, any letters with an arrow on top, or you can just bold. You can have a bold letters if you don't want to put an arrow on top. So but a scalar is any letter written in anyhow without a direction, just like C, D, whatsoever. So they can be any letters. So now, introduction to vectors. Let me enlarge the screen. So now, introduction to vectors. Bear in mind that the heart of linear algebra is in both two basic vector operations, namely vector addition and scalar multiplication. So is an addition plus and star, which is a scalar multiplication. So these are the cornerstones of linear algebra. The cornerstones of linear algebra are the two basic vector operation, namely vector addition and scalar multiplication, meaning that we can be able to add two vectors and we can also be able to multiply a vector by a scalar. So now let's talk about vector addition individual. Let's take the individual operations. So now vector addition. Suppose we have two vectors u and v inside two dimension. So because this is the two dimension, R2, it is just the dimension. It means that these two vectors has two components. The components of vectors are two because they are in two dimension. They are in R2. In other words, they are in XY plane. Like these x-axis, y-axis, two components. So they are in R2. So they are in XY plane. Suppose we have these two vectors u and v in R2, then we can add two vectors like this. U plus v is equals to, you know what we have. This is a vector with two components, which is u1, u2. They are components. So the components are written inside. So there are two notations of a vector. A vector can be represented as a column vector, or it's like this. We can say u is equals to u1, u2, where these are components. We can say u is equals to v1 u1 u2. So you can represent a vector as a column vector 2. So now u plus v can be added together like u1 u2 plus v1 v2. Those are the components. You add the component wise. That's what you do. You add what you call component wise. So you add what you call add corresponding components. You add what you call corresponding components. So u1 with v1 and u2 with v2. That's how we add two vectors, and that's what is definitely happening here. So now that's simple. We can take any two vectors. For example, if we say u, example, if we say u is 2 and 3, v, or let me write it in a new script. If we say u is 2 and 3, and we say v, it's negative 1 and 5. So we can add two vectors like this, u and v, like this. U plus v is 2 and 3. They are vectors in R2, plus minus 1 and 5, which is equals to 2 plus negative 1, then 3 plus 5. This is just equals to 2 minus 1, which is 1, and 8. So this is a vector u plus vector v. That's what we're simply talking about. So now, going on, we have what we call scalar multiplication. So the scalar multiplication is all about multiplying a vector with a scalar. Suppose we have two scalars, c1 and c2, belonging to a real number, because scalars are real numbers. That's what cause scalars are real numbers. Bear in mind that note NB, scalars are always real numbers. Scalars are always real numbers. So suppose we have given these two scalars belonging to real number and vectors u and v in two dimensions as previously. Then we multiply c1 and c1 and u and c2 and v to get what the following. So it is c1 multiplied by u, which is c1, and we put that vector with two components u1 u2. It equals to, we multiply what we call the corresponding what? Corresponding components. We multiply we multiply corresponding, or let's say each corresponding component by a scalar. So that's what to do. That's what is happening. That's why we've got c1 multiplied by u1, which is c1 u1, then c1 multiplied by u2, which is c1 u2. And also this same applies to v. You can do the same thing, c2 times v, a vector v, it equals to c2 into v1 v2, which is just equals to c2 v1, then and the c2 v2. So we multiply a scalar by a vector in a certain dimension. That dimension will still be the same. The dimension won't change. If we're multiplying a scalar by a vector in a certain dimension, the dimension remains the same, but we just multiply each corresponding component by that scalar. So that's what is happening. Now let's talk about a well-celebrated subtopic in linear algebra called linear combination. So let's talk about linear combination. So the linear combination is the sum of, or is the combination of vector addition and scalar multiplication. So the sum of C1 U and C2V, that is this guy. So if we add them together, this is what called the linear combination of two vectors, which is what? Vector U and vector V. So we have these scalar multiplication. So the moment we add them together, now they form what called a linear combination of U and V. For example, if we have got U plus V, then we're multiplying them by a scalar which is C, like a colon vector. This is the same as, you can write it as the same as like this is the same thing, there's no problem. And also this one you can write it as 2 3 is the same thing, there's no problem. So U plus V equals to C1 into a vector with two components 1 1 plus D, a colon vector with two components 2 and 3. This is equals to, just we multiply here, this multiply by this component wise. So we multiply each corresponding component by a scalar C. So this is C because we multiply 1 by C and 1 by C, plus multiply each component by D, 2D, 3D, and we add them. So that's what we call the linear combination, adding the two scalar multiplication together. This is a combination with scalars C and D. So that's what we're talking about. So you can also write this thing in the, represent this thing in this way. We have what call U is, for example, plus V. This is just equals to C. You can say it's just a 1 1 plus D. You can just is 2 3. This is just what called C when you multiply each component, plus 2D 3D when you multiply. So this is just equals to, we know how to add the vector addition, two vectors. Then we add the corresponding components together. This is C plus 2D together, this one plus this one, then C plus 3D together. And this is a combination with scalars C and D. So that's how what we're talking about. So now another example we can give it here, which is U plus V. This is just 1 1. We can also denote it like this, plus 2 3 denoted like this. This will be equals to 1 plus 2, which is 3, and 1 plus this one, which is just 4, which is just what we call this plus this, which is just 1 plus 2 3, 1 plus 3 4. Then this is a combination again with C equals to D with two scalars. This scalar C equals to scalar D equals to 1. They are just 1. So that's what we are talking about. So let's talk about a vectors and linear combination. As I said before, there's an important point that we want to highlight here. So is that a linear combination, it's all about combining addition, vector addition, and scalar multiplication. It's all about combining what? Vector addition and scalar multiplication. So when you combine these two, we now form what we call linear combination. So this is defined also mathematically above. We define it there. So now, for special linear combination, let's talk about the special linear combinations. Let's talk about special linear combinations. Special linear combination. This is a simple linear combination. We've got what called the sum of vectors, which is just 1 times U plus 1 times V. These are sum of vectors. We've got the difference of vectors. This is just with scalar, or with the same scalar, which is 1. 1 belongs to real number. Remember, we told you that the scalar is always a real number. So now we've got a 0 vector. You know what is a 0 vector? If we talk about the 0 times U plus 0 times V, it becomes 0. So now we also have got what called C times U plus 0 times, this is a vector CU in the direction of U. That's a simple thing. You know that this is going to tend to 0. So a 0 vector plus a vector, because this one is also a vector, is also that vector. So that's the special linear combinations that we can talk about. So now you know what the dimensions of a vectors. So now let's just go through the review of the key ideas. So what is really happening here? So the review of the key ideas of what we have covered so far. So now a vector V in two-dimensional space has two components, V1 and V2, as I demonstrated above. So now